Welcome everyone. Today we're going to talk about in-context learning, which is one of the emergent capabilities of large language models or transformer models that was discussed last time in connection with scaling laws. And today I want to introduce what in-context learning is, and we'll see how far we can get in formulating this kind of learning in the context of statistical learning theory, so a bit more formally. So the outline for today's talk is that I'm first going to just make a few remarks about regression versus classification. Because I'm still angry at Reviewer 2 from one of our papers for making a big deal out of this. A definition of transformer models. And 3, then we'll be in a position to talk about in-context learning in some more detail. Okay, regression versus classification. So most of the time when we've been talking about neural networks in singular learning theory, it has been thinking about neural networks as a class of functions from which you can construct a class of models, and those models are attempting to perform a regression. So in machine learning, a distinction is made sometimes between, I'm not going to write these again, this is R and C, okay? Regression is about modeling a conditional probability distribution where y, the output, is continuous, and classification is about y discrete. Now maybe there's some more fundamental reason to care about the distinction between these two things. But from a theoretical point of view, say the point of view of reading Watanabe's book, we really don't care. They're both just measure spaces. At least that's my take. Maybe Edmund can correct me.
I guess, like in the context of something like decision trees, they will be really different. At least when we get down to the nitty-gritty details of how to implement things. But yes, from kind of a model point of view, yeah, I agree with you there.
Yeah. So from a high-level theoretical point of view, what kind of measure space your y's live in is just a detail that is hidden, and you just take it to be a measure space, and then you formulate. It's just wherever you see an integral, it's now a sum, but who cares? You just write integral qy dy, and the measure takes care of which one of those two it is. As Edmund said, from a practical point of view or an implementation point of view, it may make a very big difference. And that's to some degree what I want to talk about now. But I just wanted to make the point that at a high level you can read Watanabe's book, and it talks also about classification, if you like. There really isn't a distinction at that level of theory. Okay. So now let's turn more precisely to the class of models or regression models that we're often talking about. So we're often taking a parameterized function with parameter space W, And then we formulate what we might call a regression model if we wanted to use one of these terms. And that's Px, y given w, something like this. Right, so we've had many talks in this seminar series that start from this form of conditional probability distribution and then perform some kind of analysis on it. And this is how you would go from this kind of parameterized family of functions to a class of regression models. So here y is some continuous variable ranging over Rm. So now I want to explain how you might go from, instead from a parameterized family of functions, say a neural network, which is often what we're considering, how you would go from the same starting point, but instead of producing this distribution over Rm, to produce a distribution over a discrete set. We might as well take the discrete set 1 through m, which I'll write in ordinal notation like this. Okay, so I'm going to motivate this with a little bit of, I wouldn't say it's a derivation exactly, but kind of Bayes' rule argument. So we're leading up to the softmax, which we've sort of arisen earlier when I described transformer models, but now I'm going to sort of introduce it more carefully. Okay, well, if we're to have some distribution y over this discrete set, then by Bayes' rule, we have this. Now, since the values of y are finite, we can just write this as a sum. And so just by substituting all right. So the point of this reformulation is that we can, instead of thinking about this distribution over a discrete set, think about this family of continuous numbers, or rather their logarithms. So we can model with our parameterized family of functions f the probabilities that arise in this formula. So these px joint with y equals j's. Or assuming they're all non-zero, which we will. Actually, this is a bit of a technical point that may be non-trivial actually in SLT. So I said that, who cares whether they're discrete or continuous distributions? The place where I think this actually becomes a genuine mathematical issue is to do with the boundary of the space of probability distributions, which you don't have to worry about in the case of continuous distributions, but actually plays a role in discrete distributions. If you're interested, Tom Waring's thesis has a bit of a treatment of this. You have to resolve the boundary of the space of parameters in addition to singularities to properly treat the RLCT in these settings. So this is like actually an irritating and potentially meaningful complication. I don't want to get too far into that today, so I'm just going to assume that all these probabilities are non-zero, or what's the same, that we're in the interior of the space of probability distributions. Okay, so if I want to model this distribution of m categories or classes, I can model the logarithm of these probabilities. And I'm going to call those Lj. And it's traditional in the machine learning literature to call these logits. I don't know if that's an older statistical term or where this came from exactly, but this is a widely used terminology. So the logits, if you take them as a vector, so what possible vectors can you get out of, so if you imagine all possible conditional probability distributions over the ordinal m, and then you take the logarithms of these probabilities, what possible vectors can you get out? Well, so let's investigate that a bit. So if we rewrite the original probability distribution in terms of these logits, what we've got is what's called the softmax. So the softmax takes as input a vector of size m and outputs a probability distribution on this m element set, where a tuple Lj, j1 through m, becomes the probability distribution where take the exponential of Lj. So the exponential of Lj is, of course, the numerator on the previous board. And then the denominator on the previous board is the sum over I equals 1 to m, all the exponentials. Okay, so this denominator is the same for every j, and it's just the numerator which varies with j. So this mapping from logits to probability distributions is called the softmax. Any questions so far? All right. Okay, so this is surjective. Onto the interior. What do I mean by the interior? Well, the set of all probability distributions is a simplex. Think about all the constraint. So it's a tuple of non-negative real numbers less than or equal to 1, which sum up to 1. That space sitting inside Rm, its boundary inside Rm is going to be where any one of the probabilities is 0. So the interior is the set of probability distributions where all the probabilities are strictly between 0 and 1. So that interior, if you give me any distribution in that interior, then clearly you can take the logarithms and construct some logits which map onto that. And I'll more precisely, so if you give me a tuple, all of whose entries are non-zero, then to construct the distribution, right? So given some so if you start with these logits, then you can recover the logits by noting that if you take pj to be the jth entry in the distribution, then log pj, so that'll just give you lj minus some stuff, and the stuff is the same for lk, so you just get a cancellation. Okay, so you can recover from the probabilities by taking logarithms and differences, the differences between all the entries of the logits. But hopefully you're starting to see that this map is not injective, far from it. Right, because if I take softmax of some tuple L and I add some vector of constants, then the C's are all going to cancel out. Right, I'll get this common factor of e to the c in the numerator and denominator. So even before we get to degeneracy in the model, the F part of constructing these conditional distributions, we already have this degeneracy just arising from the softmax. Okay, so, but it's easy to see, the proof's in the notes, it's not very interesting, that apart from this degeneracy, softmax is injective. So if you consider the diagonal subgroup of R to the M, which just sets C as this constant vector, and mod out by that subgroup, so identify two tuples that differ by such a constant vector, then the softmax is a bijection of that quotient with the interior. Actually, I don't know if that's a homeomorphism with the quotient topology. It probably is. Okay. So the conclusion now is that given a parametrized family, we can also give a classification model that predicts classes by the formula py given xw is softmax of f of xw. And this is the predominant way that neural networks appear in, say, language modeling. Actually, most of deep learning is about classification rather than regression. That goes back to the original tasks in which deep learning excelled, which was image classification, where M would be the number of possible categories for images, cat, dog, train, etc., through to the modern day where language models are predicting tokens. So which token is the next word? Well, the model needs to predict, well, it outputs a probability distribution over possible tokens, and that is the prediction which is attempted to be matched to the truth by a cross-entropy loss. Okay, so this is how neural networks give rise to models in the context of deep learning predominantly. It's classification. Now, I want to make a brief remark about that loss that I just mentioned. So what happens if I take the KL divergence of a model produced in this way with a one-hot distribution, as you'd call it in machine learning, which represents the true category for a given input. So that's the next few minutes. But are there any questions about the softmax first? All right. Yes, let's do a little calculation. So let's take the characteristic function of the jth class. And suppose we're using this model and the true distribution for a given input x is this one-hot vector, as you would see it formulated in, say, PyTorch or TensorFlow. Okay, well, if I take the KL divergence, maybe I shouldn't say KL divergence. I mean, the problem with there's a few technical problems here, right? We shouldn't really allow this thing. If I want to take the KL divergence against this, then I'll end up with logarithms with zeros in them. So I should put tiny deltas in all the zeros and 1 minus delta or something. Let's just leave that annoying question for later. Actually, I don't know the correct way of dealing with that. I've in the past theoretically considered that by putting those deltas in and taking limits. That is legitimate, but actually I don't. This is related to the earlier technical question about boundaries and how to deal with them, and something to come back to at some point. So the cross entropy just basically renormalizes by getting rid of this infinity we'd get from the logarithm of 0. The cross entropy, remember, is where the KL divergence has this numerator in it, right? Maybe I'll remind you. Okay, so that's the KL divergence, and you can split it into a part that has this numerator, which is negative the entropy, and a part that just compares px to qx like this. And that's negative the entropy of q plus, I'll just call it CE for cross entropy. Okay. So the cross entropy of this one hot characteristic function distribution with our conditional distribution. Okay. My iPad just crashed. A moment, please. What say you, Edmund? What's the principled way of doing classification and avoiding these infinities?
I was wondering whether or not it's well defined, since it's a 0 log 0 scenario, isn't it?
Yeah, that's right. So obviously it's not well defined, but the question is, what is the right way of thinking about this? I mean, I guess from
sorry, I was actually saying it is not well defined.
Oh, it's not well defined. Oh, I see. You're saying the
0 log 0
zero.
is yeah, so like taking limit from the positive side, because we are dealing with positive numbers. That seems to be okay.
Yeah. I guess you just have to be very careful manipulating expressions if you have this special definition of 0 log 0, I guess, right?
Yeah.
But yeah, maybe that's right. Okay. So if I compute this conditional distribution, so what is this? Well, it's going to be minus. Now, so this here, I've got, well, okay, this is a bit confusing because I've written it with just an x up here. So maybe I need to get rid of this and start again a little bit. Because there's an x and a y in the distributions I'm talking about. Okay, maybe let me just write it as the KL divergence and then just take Edmund's suggestion to blithely delete the terms I don't like. Okay, so we have, I mean, the way we think about all these distributions fundamentally is as joint distributions over the input and output, which we refactor as conditional distributions. So this, by definition, is what the KL divergence is between our model and the truth. Wait. Okay, this is for all x's. I shouldn't do it like this.
Yeah, the j should be a function of x or something.
Yeah, j should be a function of x. A function of x. Yeah. Okay, so let's do that.
Did you mean to swap the given that symbol and the p expression?
Which p expression? Oh yeah. That is meant to be that way. Okay. I'm going to put it back to the way it was in a second. So,
which means it should be that way on the left hand side as well, I think.
Oh, sure. Yeah.
Yeah, it's like different. Yeah, okay.
Yeah, that's fine. Yeah. Thanks. All right. Okay. Now, this thing here, this qy given x, is what we're assuming. Well, yeah. I guess I need to put like a qx over here or something, right? This is 1 Okay, so we're only going, so this integral over y just collapses because I have this delta function here, right? So this is really just an integral over x. And then this numerator here is either 1 or 0, depending on the value of y. Well, this integral over y is really a sum, first of all, right? So that numerator is either 1 or 0. The 0 terms I'm ignoring because I'm ignoring the 0 log 0 terms. And so I'm left with 1 over p, the correct class for that given input, dx. Okay, so finally this is well, what is py equal jx given xw? Well, that's given by the left-hand board, right? That's given by this expression here. So if we just substitute that in, what we get is fxwjx minus the log of the denominator. All right, so this is the KL divergence between the model and the truth, and it's the quantity that, or the loss, and it's the quantity that we would estimate based on a sample and try and decrease in order to fit the model to the truth. Okay. Notice that with this particular true distribution, this is unrealizable because you'll never make this actually 0, right? So this quantity here is negative. And if you take its exponential, you'll see that it's 0. That is, the KL divergence will be 0 exactly when 0 is equal to the sum of the i's not equal to jx e to the fx wi for all x. And the right-hand side is a positive number, so you'll never make this equal to 0. You could make it realizable, I guess, by perturbing this a little bit. But this is the part where I'm actually unsure about how to deal properly with this. So I guess a classification problem from a pure Bayesian perspective is just mistaken fundamentally. You can't have the truth have 0 uncertainty in these other categories or something like that. So maybe the answer is just to reject the question. But I don't actually know the best way to think about that.
Dan, I got a quick dumb question.
Yeah.
How'd you get from here to here?
Yeah, just using Bayes' rule in the numerator and denominator.
Oh, right, there's Bayes' rule involved. That was just okay. Yeah, cool. Thanks.
Yeah, so I guess the denominator is
right.
Yeah, and I'm replacing the px. We're assuming the distribution over x isn't being modeled, so that's just qx. Yeah.
Oh, yeah, that's right. Oh, right. Px given w is just q in that case.
Yeah, that's right.
Okay, cool. Thanks.
Other questions?
Maybe a question, or I don't know, maybe more of a sharing, which is that it's an interesting case where the continuous world is kind of colliding with the discrete. I'm accustomed to transforming between distributions that agree on what is possible and what is impossible. Like that's a requirement for a Radon-Nikodym derivative to exist between two distributions. But in this case, there's the one hot truth is saying that everything is impossible apart from one category, given zero probabilities. So I don't know. I don't want to hold you up, but carry on. But it's
Yeah, I agree. I also find this. I mean, I suppose it makes sense from a more applied point of view, because, well, I just want to minimize my loss, and I could put the tiny numbers in there, but it wouldn't change the direction I actually go to minimize the loss. But I don't know how seriously to take it, I guess. So you can just put the deltas in there and get a KL divergence, and then maybe that has a valid limit as delta goes to 0, and then you call that your KL divergence, and maybe there's a more principled way in which that is correct. This is kind of an active theoretical issue for me, because with Tom Waring, a former master's student of mine, and James Clift, another former student, we care about singular learning theory in this setting. We're sort of considering models based on continuous relaxations of Turing machines and things like that. And it actually is. It's hard to know how seriously to take it. I feel a bit unsettled about my current level of. I mean, I think I have it. I think I could do various technical things and make the problem go away, but I feel like I don't have a satisfactory way of thinking about it. Yeah, thanks for the comment. Okay, so the next thing I want to do is to give a definition of transformers. So the reason I preface that definition with this discussion is that the transformers will make use of the softmax. So the transformer is a neural network. It will output a vector, and that vector will be used to produce a family of distributions, which are the things that are viewed as the output of the model in terms of a distribution over possible words. Okay, so we're going to move over to the next set of boards to give the definition of the transformer. Actually, we'll move around completely around here. All right, so as you can see, I've pre-populated this with an algorithm that I took from Phuong-Hutter's paper from this year, I believe. The reference is in the notes that I posted in the Discord. I think it's Formal Algorithms for Transformers is the title. Of course, they didn't invent transformers, but as a mathematician, if you try and read the transformer paper, you'll be left wondering what all these terms mean. And this is the only self-contained reference that I know that really spells things out in a way that is seems nice to a mathematician, so a highly recommended reference. But before we get into that reference itself, maybe I'll just draw a picture of how you're supposed to think about a transformer model. And I've drawn this picture before, but I think it bears repeating before we get into the formal definition. So a transformer is a neural network. The neural network will take as input some number of tokens, say L. So a token is an element of a discrete set. So you can think of it as a category in the following, in the previous discussion. So tokens are elements of some set like that. They would be, roughly speaking, parts of words. The first step a transformer is going to take is to transform those tokens into something continuous. So that's the embedding step. And the other boards say exactly what all these steps mean, and they're sort of color-coded with green and blue. After you've changed the tokens into vectors, so an embedding is a learned mapping from discrete tokens to vectors. After those vectors are produced, they're then processed through multiple layers of the actual transformer, what's called the transformer block. And it's not a mistake that I'm not drawing the arrows from right to left. I'll get to that in a minute. So in the original literature, these were called transformer blocks. I notice that these days people just refer to them as layers. And I'm going to say more about what they are. But for right now, I just want to say there's going to be L steps that look like this. So iterated transformer blocks, which take those original vectors associated to the tokens and kind of update them with information from other tokens. So they sort of incorporate the context is how people usually think about it. All right, so once that processing has been done, there's then an unembedding step, which is a term I hadn't seen before Phuong-Hutter's paper. I quite like it, which doesn't map back to tokens. Maybe that's a reason to not like the terminology, but it's just a final feed forward. Well, there's just a learned mapping that is applied to every token, and then there's a softmax. Okay, so this is all one thing. Maybe I shouldn't draw it like that. The softmaxes are all independent. Okay, so each of those vertices is going to have a value after the calculation, which is some vector in Rm. M is the number of possible tokens. And then we apply a softmax, and what we've got at the end of that is a sequence of probability distributions. And the way to read this, so this is the teeth entity, so that's 1, 2, up to L. The teeth entity, the probability distribution that you get out at the end, you should read it as the probability of, excuse me, I guess this is what I was calling Y before, right? Yeah, with apologies, I'm going to switch to X just because that's the way the formal definition is written. So the probability distribution you get out at the teeth column is interpreted as the conditional probability of the sort of next token being a given value, given all the previous tokens. Okay, so then you can see how this, you just factor the joint distribution over all the tokens into a product of all these conditional distributions. Okay, so to explain what's going on here, I need to tell you what the transformer block is doing and why, for example, these arrows only go forward. And the way to think about that is that time goes to the right. Well, strictly speaking, there's no time in the model, right? All the tokens are fed in all at once, and time is only manifested in terms of how you allow entities, the name for these vectors that sort of appear associated to these nodes is entities. Time appears only in the convention about which entities a given entity is allowed to attend to or receive information from. So that's how time appears. Now, you interpret that in the situation of text, for example, as being earlier text comes earlier in time, right? You're sort of reading from left to right, token by token. Okay, so are there any questions about this diagram before I go and give a formal definition of these ingredients? Okay, so let's take a look back here at the first board. There's many variants of transformers. The original transformer from 2017 is now referred to as an encoder-decoder transformer. There's BERT, and there's many variations. Some of them are enumerated in the paper. I'm just going to focus on the one that appears in GPT-3 because that's the situation in which we've discussed in context learning, for example, last seminar. And the decoder-only transformer works as follows. So it's a neural network. The vector of parameters is denoted theta. The input is a sequence of tokens, x. The output is going to be a sequence of probability distributions, which, as I said, is interpreted as a sequence of conditional probability distributions of the next token, given the tokens up till now. You'll notice that they use in the paper this kind of Python notation. So we would write x sub t, and I did that on the previous board. They write x bracket t, and where we would write x1 ... xt, they write this kind of slice notation. There's various hyperparameters. I maybe won't stress on all of them, but you've seen capital L, that's the number of layers. Yeah, let's just skip over those for now. Okay, so here's how it works. L is the length of the input sequence, as I said before. For each t in bracket L, and again, this bracket means the same as what I said before. Okay, so you loop through all the incoming tokens, and you apply this rule to the token. Okay, so how does this work? So this notation means the teeth column of WP. Now WP is one of the things in this parameter vector. So any unexplained notation, so WP, WE, gammas and betas on the next board, the curly WL that you can see over here, for example. What else? These WMLPs and BMLPs. These are all vectors or matrices of weights that are actually trained during the training process of the transformer. So those are parameters. Okay, so I have some matrix of parameters, WP, and the teeth column is what I'm extracting by this notation. And I add that to the X teeth column of WE. WE is the embedding matrix, and this term I've just underlined is this thing that I mapped the teeth entity to in my picture. Right, so to go back to my picture for a moment. So if this was the teeth entity, it gets mapped to the vector, which is this WE colon X T. Right, that is the starting vector which is associated to the token at position t. The token at position t is xt. Okay, so what's this sum? The first term in the sum, hopefully I've explained. That's just the vector which represents that token. The second thing is a positional embedding, which allows the network to know where in the input that token is. And I'm not going to, it's important, but I'm not going to say much about that. It's kind of irrelevant to the discussion about in-context learning, which I hope to get to. So the result of adding those two is the teeth entity, ET. Then you take all those entities together, you get a matrix, that's X. And then you process X. And this processing you do L times, that's the transformer blocks that I was mentioning. So this stuff here is the transformer block. I don't want to say anything about layer normalization. It's not very interesting for our purposes, although it is essential to make the whole thing work. Conceptually, the main ingredients here are the attention and this feed-forward part. So attention, I've described a few times. Maybe I'll mention briefly how it works again in a moment. This is where entities, entity T, receives signals from entities 1 through T. So that's what this masking business is about here. And it receives signals. Okay, maybe let's describe this on some free space if we can find it. Yeah, here. Okay, so how does attention work? All right. So you've got entity T at some layer, and that's going to be updated from all the previous entities. So it's supposed to receive information somehow from them. And the way that's going to work, in the algorithm it's called X. So X is a matrix, and its teeth column is the current representation at this layer of the transformer of the teeth entity. Right? So somewhere back down here at the beginning of time was this ET. And then it was processed, and now it's this thing, X colon comma T. Okay. So how do I aggregate all this information to generate a new version of the representation for the teeth entity, which is the X? Sorry. Yeah, well, I won't give it a name. So first, I don't actually remember what it's called in the Phuong-Hutter paper, but so it's probably WQKV, something like that. So take the ith entity, you apply a linear transformation to it, and you extract and you split that output into 3 vectors, which you think of as query, key, and value. I'm doing the one-head version. There's multi-head attention. That's what the MH stands for. But let's forget about the multiple heads. It's not much more complicated. So then what you do is you create a softmax distribution. So the teeth entity is going to, with some lambda, apologies, I was using I before for this. Okay, so that's the new value that gets put. That's the output, so to speak, for... Oh, what's going on here? So this thing here is a matrix. Its teeth column is going to be what I just described here. Okay, lambda is some parameter. Just for technical reasons, it's the square root of the size of these vectors, q's and k's, but it's not really important for us. So the way to think about this is that you extract from the current representation in this layer, you extract some value. So this is vt minus 1, v1, and you propagate those values to update the representation for the next time step, and the ones that are more relevant are propagated with a higher weight, and the relevance is determined by how aligned some query vector is for t with the key vectors for every other entity, and those which are strongly aligned will have higher dot products and contribute more to that sum. So in this way, the transformer routes information between entities in order to update them over multiple layers. Okay, then there's this final step, which is just a feed-forward network. So there's a final feed-forward MLP. In this case, just one layer. GELU, it's not important, it's just some nonlinearity, so it's kind of a refinement of ReLU. Yeah, what else to note about this? One thing to note is that the original X is preserved somehow, right? So what you actually learn is the delta. So you learn what to add to the original representations in order to compute the next layer. Okay, and then I haven't quite finished describing the transformer. So after you've done these L layers, then you come to this part here. So what do? You apply layer normalization one more time to all these vectors, one for each entity, and then you apply a linear transformation to each one, and then apply the softmax. And that gives you these distributions over tokens. Right, any questions?
How many layers are common?
Oh, good question. So it depends on the application. If you're asking about GPT, I think it's... Oh, I'd actually have to check. Yeah, let me do that. That's a good question.
Well, I can easily... Again, I don't want to hold things up. I can look it up afterwards. It's just
No, that's, I think it's probably several hundred to 1,000, that order of magnitude.
Yeah.
Okay, so GPT-3, so GPT-3 with 175 billion parameters has 96 layers. So no, I was off by an order of magnitude. That's so 96 layers. The number of heads is 96. The dimension of the model, so I think that means the size of the Q, Ks, and Vs is 12,000.
Thanks.
Yeah. Other questions? Okay, so now I have the vocabulary to define in-context learning. So I don't think, the first time I noticed this terminology was in the GPT-3 paper, which is, the title is Language Models, a Few Shot Learners, from OpenAI. Maybe I think it's a pre-existing term, but they certainly that's really the focus of the paper, is this capability. All right, well, what is the context? Well, if we have token string x, which is x1 through xt, then in predicting token t plus 1, x is the context. Right, so if we go back to the previous board, the context is just all the things that are somehow the things on which you're conditioning to make the next prediction. So in this box here, you're predicting this token, and all these tokens are the context. Now, as you move to the right, the context is getting larger, right? Now, while that's strictly speaking correct, when we're talking about in-context learning, generally what people mean is the following kind of refinement of that, where some initial sequence of tokens is viewed as the context or the prompt. So so you would say you have some initial token string, and then in predicting token t plus 1, t plus 2, t plus 3, and so on, the context is x. Now, what does it mean to predict all those tokens? Well, so here's how you would think about it. So suppose you start with some number of tokens. I guess I've written it t. I'll stick with that. Okay, so you run those through the transformer, and you get out these probability distributions, and then you sample. Right, and now you've got a new token. And then you put that back in the beginning, and then you run the machine again. That gives you a new distribution, and then you sample from that distribution. And that gives you a particular token, xt plus 2. And then you take that token and you feed it back to the beginning, and you run the transformer again. So that's how you make a sequence of text using, say, GPT-3. So if you open up GPT-3 on OpenAI's website, and you type some text into the box and you click generate, what's happening is that the text you enter is this initial sequence of tokens, x1 through xt. So that's called the prompt. And then it's going to generate the rest by first predicting the next token, and then taking that as the context to predict the next token, etc. Right? So in-context learning is the special case of this generating text, where the prompt is sort of deliberately engineered to be a family of data points, in some sense, for a pattern that you wish the model to learn. So, okay, so that's the context. In-context learning refers to the situation where the prompt is explicitly, it's hard to say exactly what counts as in-context learning and what doesn't, obviously, but at least we can say that we call it in-context learning when the prompt is explicitly designed to have input-output pairs or some kind of pattern. All right, so for example, maybe X is the following sequence of tokens. So let's imagine some function which takes a string and returns a sequence of tokens. Just putting in new lines. Okay, so that's a sequence of tokens, and GPT-3, so that would be the prompt, and then you would finish by sort of framing a question. So you would say something like 6 plus 2 equals n string. And then if you do the generation part, yeah, hopefully it will give you the right answer. But you can do quite complicated learning tasks in this way. All right, so that's in-context learning. And the question I want to pose, and then we can discuss this. So what is the formal definition of in-context learning? In the framework of statistical learning theory. Say singular learning theory. And we're used to in SLT formulating this in terms of triples or quadruples, right? Where you have a space of parameters, you have a true distribution, you have a model, and you have a prior. So what are all of these things in this situation? Yeah, let me see if there's anything more I want to add before we just start figuring out if we can answer this question. Maybe I'll remind you what I hope it's clear that the transformer itself is a statistical model. So the space of parameters is the space of thetas, right? So if we go back to the definition of the model, so all these weights, the value of all those weights is the theta. The true distribution is the sequence, or the set of sequences of tokens. So maybe I should say how a transformer is trained in order you can infer the true distribution. You can infer what the definition of a set of samples is from the training procedure. So usually you would fix the context length. So say for GPT-3, I think it's on the order of several thousand tokens. Okay, so what is the loss? Well, for each position in the sequence, you generate this conditional probability distribution P of xt plus 1 given x1 through xt. And then the loss is a sum over all those positions of the cross entropy of that distribution with the true one-hot distribution of which token appears at that position in that sentence. So you take a set of sentences or sequences of strings from, say, the internet, English language. That gives you many sequences of 2,000 tokens. And then you know at each position what the true token is, and you take the cross entropy of that one hot distribution against the conditional distribution output by the transformer on that sequence of tokens. And you add over all the positions, those cross entropies, and that's your loss. Okay, so the true distribution is all these conditional distributions coming from actual text, whatever you take that to mean. The model, well, I've described how the model is computed, how these conditional distributions are defined. The prior, I guess, is baked into the not normalization, initialization procedure for the weights. So generally speaking, it would be something like, actually, I'm not quite sure what they use these days, but it's probably, you would look it up under Glorot initialization or He initialization, some kind of Gaussian distribution centered at 0 with a standard deviation depending on how deep it is in the model. Okay, so that's the transformer itself so it's pretty clear how to formulate that as a formal model in SLT. But yeah, in what sense is this like a nested model? This in context learning. Right, any thoughts about that? I can try and think out loud. I really genuinely haven't thought about this. I'm not even clear on what the space of parameters is. And what comes to mind is like a nested model where you fix parameters in, so you have a mixture model, a mixture of 10 Gaussians, and then you fix some of the parameters, and that's again a model. So what you're doing by fixing these input-output pairs is you're kind of fixing some of the entities that are fed into the attention, right? So you're not exactly, it's not like a nested model in that sense where you're fixing some parameters. You're doing something a little bit different. Maybe I can.
I have a question.
Yeah.
So the term in context learning, does it refer to the fact that the model can perform? Is it referring to the phenomenon that one shot is better than 0 shot, 2 shot is better than 1 shot, 3 shot is better than 2 shot, etc.? Or is it referring to the phenomenon of the fact that you can use the model this way, as in make it predict the next token? Like the second part is a much more abstract concept of the training procedure of just predicting the next token. Somehow learn in the very colloquial sense other skills like addition.
Yeah. Actually, I find the way that these terms like few shot and one shot are used to be quite confusing. I think so I believe in the GPT-3 paper they actually do refer to the situation I've just outlined as, maybe this is few shot. Let me just double check.
Yeah, that was the sense in which I was using it.
Yeah, they call it few shot, but this, I mean, I think elsewhere in NLP, this also refers to just where you're, I mean, this has some other meaning, I think, potentially. Or at least yeah. What's the name for it when you take... Oh, no, that's like top K. Okay, maybe it doesn't have some other meaning. Yeah, sorry.
I guess
repeat your question?
I guess kind of a more concrete question here is that the learning, the word learning in context learning has nothing to do with training, as in there is no more
That's
actual
correct.
updating of weights.
Yeah, that's correct. Yeah. So a nice diagram that they draw in the, I think it's the first page of the paper, is they draw as horizontally like weight updates. And then they draw vertically this in-context learning. Just to make clear that these are not related. So this is giving these examples. So that's right. So when we do the training and then we fix the weights, and then we provide these prompts, and different prompts give rise to different behaviors on the next token. So the so that's the sense in which in-context learning is intended. So you could say, well, is that learning? Well, I mean, it seems to me to fit at least the definition of what it means to formulate a model in statistics, right? I mean, it's a procedure for going from data samples to a model, and that is happening here, right? I give you data samples, and then the model that you get by fixing this prompt or this initial tokens is a different model to the one if you don't add any tokens, you don't prefix your input with any tokens. It's not going to give the same predictions, right? It's like selecting from that. The transformer that was trained by SGD is like this. You could think of it as a kind of library of models among which you're selecting by providing these initial prompts. It's not like they're different models, but you're certainly priming it to behave differently. So it is a mapping from data to models.
So it's an algorithm that turns input-output pairs into a model that given future inputs produce more correct outputs.
Correct.
And the algorithm takes as input a trained large language model and examples.
Yeah, that's right.
Okay.
And they have a graph in their paper showing the difference between 0 shot, 1 shot, and few shot. As you increase the number of examples, the performance improves, a bit like making n go to infinity. So, it's kind of suggestive. I guess given the time, we probably don't have the space to answer this question. Maybe that's fine. Let's come back to it next time. But before we wrap up, are there any ways I can clarify the situation so you can chew on this over the next week?
I think I need to read.
Yeah. The Brown et al. The GPT-3 paper is quite clear, I think, so that's recommended. Okay, if there aren't any questions right now, then I think we'll wrap up. Thanks, everyone. Ben, I can't hear you, no. Maybe you can type in the chat if it's short. Okay, no problem. Okay, thanks everyone. See you next week.